Thank you very much, Tavi. Thank you for organizing this. Thank you for allowing me to participate. I'm Eric Rignot, and I'm going to talk to you guys about the grounding line, this elusive boundary where ice meets with the ocean for the first time in its history. This transition boundary is very important for the evolution of glaciers. It's the boundary of interaction between ice sheets and the ocean system. It's the most difficult to study because it's typically within, below a kilometer of ice in very deep cavities. None of us can freely swim there. We don't know what it looks like, but there's a depiction here by cartoonist Michael Dormer, of what it might look like at the grounding line. We have this a party at the grounding line with some strange creatures with special ears that can adapt to this depth, and having a rock concert down there. So I know several previous speakers have been reflecting upon the impact of the pandemic upon our work, upon our health, mental state, and reflected about the pause of people in famous pictures. For me, a way to escape the stress of this pandemic is to imagine that I could go to the grounding line and become and have a rock concert, become a rock concert, and be able to sing some songs of freedom at the grounding line. So this is the title of this talk.
Sorry, I wasn't listening. Apologies for that.
On keep rocking at the grounding line. Before I get into this, I want to dedicate this this presentation to two dear colleagues who left too early recently. You probably all heard about Connie Stephan, who had a tragic accident in Greenland. He was a famous scientist, a great friend of 30 years. We did a lot of field campaigns together, a great human being, and he's done a lot at the international level to bring awareness on the issues of climate warming to the public and policymakers. He died the last time he was visiting Swiss Camp. He started Swiss Camp in the 1990s, and this was his last visit. And it's very unfortunate that Connie left us so early. Another friend whom you probably don't know because he's not a glaciologist is Jacob Van Zyl. He was a brilliant engineer and manager at the Jet Propulsion Laboratories. He's from Namibia, not Nambia, like I misspelled here. He was a mentor to me. I probably would not have been involved in science interferometry if I was not encouraged by him. He was a great science mentor, but he was also the one who introduced me to running. We probably run 25,000 miles together in the past 30 years, regularly at JPL and on race days, on weekends. And that shaped up my life as a scientist. You know, to be able to run is a very important part of my daily routine. And Jacob also left us very early, tragically, last month. So I dedicate this presentation to these two people. Now the grounding line, if you see here this graphic, this old graphic from 2011 on the left is where the ice detaches from the bottom. We don't always know the seafloor and starts becoming afloat in the ocean. This is actually a data plot from data along Twigs Glacier. The dotted line here represents the line of hydrostatic flotation. So the bottom of the ice shelf should be along this line if it was in hydrostatic equilibrium. So what happens at that boundary is that the ice traverses hydrostatic equilibrium, but seaward of the grounding line, it's pushed below hydrostatic equilibrium because of bending stresses. And there's a whole region quite wide, up to 10 kilometers wide, where the ice is not fully in hydrostatic equilibrium and adjusts to that. So it's very difficult to see that boundary in situ if you want to travel down there and use the GPS in the water. It's not going to be very efficient. it's very difficult to see it from above, from radar sounders, from cracks on the ice. It's been a challenge for generations to figure out where the grounding line is. But we can see it very precisely with altimetry. We can see it more precisely with interferometric synthetic aperture radar. And this is an example here on the right of deformation fringes on Zachary Strom in Northeast Greenland. Every color cycle, 360-degree change in phase represents a 28 millimeter differential motion of the ice towards the radar illumination direction. So effectively, you pick the deformation of the ice surface within millimeters as a result of change in the ocean tides that where you have seawater infiltrating beneath the ice and pushing the ice just slightly up, and you can detect that super precisely. So not only we can see where the grounding line is, but we can study how it might migrate with time, because this bed slope and surface slopes are typically very small on an ice sheet. We're talking about 1%. So any change in the height of sea level or the thickness of the glacier of about meter scale would transfer into a 100-meter horizontal migration of the grounding line. So being able to detect it precisely is important. But being able to understand how it changes with tide is also important if we want to measure long-term motion. We can't talk about ice shelves and glaciers and evolution without mentioning the marine ice sheet instability with the pioneer people who worked on that. The concept is probably known to all of you that on a retrograde, on a normal slope going uphill positively, if you initiate a retreat of an ice sheet or a glacier terminating in an ice shelf, or just a glacier without an ice shelf, you will have a negative feedback that will slow down the retreat. The flux will decrease with time and the retreat will stabilize. On the reverse slope, there's no such stable state. There's actually two states of stability for a reverse slope. Either the ice sheet goes to the edge of the continental shelf or it becomes completely afloat. So in a way, you might argue on a retrograde slope, why is there even an ice sheet? Stability is procured by ice shelves in front of these glaciers. These ice shelves act like plugs on these glaciers. They shear along the margins. They can be buttressed also by small islands and procure some resistance to flow and prevent the glacier to flow a little bit faster. I want to show a back of envelope calculation here to sort of balance out the role of ice shelves and the role of granular migration in stability of glaciers. And that concept was really brought to my attention by Bob Thomas in his paper on Pine Island Retreat, published in 2003 in Journal of Glaciology. Before that, I did not really put my nose on this the same way. So a basic rule of thumb, that was the Bob Thomas rule, is 1 bar for a driving stress, 1 bar for basal stress, 1 bar for a lateral stress on the glacier. Ice accommodates about that level of stress, and below that it does not respond, and above that it's not very happy. So if you imagine the retreat of a grounding line of a 20-kilometer wide glacier, 1 kilometer retreat, which is not exaggerated retreat, you remove a force of about 2,000 gigatons. You multiply the 1 bar by the area of retreat. If you thin an ice shelf, let's say 10 kilometer long, and you thin it by 10 meters over time, the force that you will reduce here will be only 20 giganewton. So 2 orders of magnitude smaller. If you push the experiment, you realize that you need to remove an entire ice shelf, 50 kilometers long and 300 meters thick on average, to get something close to the retreat of a grounding line of 1 kilometer in terms of the force balance of the glacier. So somehow maybe the effect of ice shelf removal is a little bit exaggerated, in the sense that in order for an ice shelf removal to make a big impact on the glacier, equivalent to a retreat of a grounding line, you really need to remove the entire ice shelf. And that concept was illustrated by Bob Thomas back then in 2003, when we were just playing removing the ice shelf in our model, when the grounding line retreat would just change the glacier even more. So grounding line retreat, extremely important in the context of the stability of an ice sheet. Now, how do we retreat a grounding line? And this is my little cartoon rendition here with a glacier with a floating ice shelf in the front with geometries that are greatly exaggerated, and a glacier terminating without an ice shelf at the bottom here in B. We can retreat the grounding line if we change the thickness of the ice, just from flotation, from hydrostatic equilibrium. If you thin the ice, it will reach flotation sooner, and it will retreat. Thinning can be due to surface melt. It can be due to dynamic thinning. That means that the ice is stretched because it's accelerating. It will thin as a result without surface melt, and you retreat the grounding line. But there could be other mechanisms. One of them is the calving of grounded ice blocks. If you remove an iceberg in front of an ice shelf, it does not affect the force balance of the glacier. Even if you do it in front of a glacier like here, but there's no basal friction at the bottom, it should not affect the force balance of the glacier in a significant way. You need to remove grounded ice blocks of ice, which can happen in occasions, but I'm not convinced it happens very often, in order to change the basal resistance in front of the glacier. And then there's a third one, which is the removal of ice directly at the grounding line by the ocean. And so for the ice shelf on top, I'm sure many of you would say, what is Eric talking about here? And for the one on the bottom, it's something that we sort of discovered more recently, looking at the glacier faces and ocean models, that the predominant way by which the ocean acts upon these calving faces is to undercut it. And we have documented evidence that this is happening. So above the undercut, all the ice above this undercut is not supported by anything underneath, so it does not procure any basal resistance. And the ice below that undercut, if any, is too thin to provide much basal resistance. So this is another mechanism that can contribute to a forced grounding line retreat. Now let's go to Twigs Glacier, the big giant in the West Antarctic system. This is the blue map, is a map of the bed topography. The transition boundary, the grounding line here is shown in multiple colors because there's different years. The big blobs represent the level of migration in the last 10 years, and the smaller blobs, migration in the previous 10 years. We have a lot more data in recent years than we had in the past. We just had a few examples of that in the past. The flow here is from the top to the bottom. The bottom is the floating extension of the glacier. The top is the grounded ice. The main trunk of Twigs Glacier is over here. The thwaites eastern ice shaft, slower moving with shallower ground, is over here. And if you look at the grounding line, actually the grounding line mapping, which we turned into a grounding zone of Twigs Glacier in recent years, where we have a lot of data, you see that the width of that grounding zone varies a lot across the glacier front. In some places it's very thin, which is sort of what we would expect from the tides, and in other places it's very wide, many kilometers wide. Now, if you remember my little cartoon at the beginning, if you have ice interacting over a hard bed, you can calculate the level of migration with the tide very precisely if you know the surface and the bed slope. And typically with bed and surface slope of the order of 1%, you expect a grounding line migration of 100 meters for a meter tide. So anything larger than a few hundred meters is not expected. And here we have areas where the grounding line migrates over many kilometers. That has been predicted by Sayag and Vorster by looking at ice interacting with a deformable bed, a bed that can undergo viscoelastic deformation during the tidal cycle. Then you can have moments where the bed sticks to the ice, moments where the bed moves away from the ice and deforms, and have larger range of migration and accommodate several kilometer migration. There's also another study by Tsai and Gudmundsson who look at granular migration as the propagation, elastic propagation of a fracture at the transition boundary, and they can accommodate also large migration. But what's important for us is that means in these areas, which typically correspond to areas of very shallow bed slopes. The steep slopes usually are associated with small grounding line migration. Typically, where you don't see much of a grounding zone, the glacier is hanging on a ridge, and over here you have a flat bed. This is a region where there's tidal flushing of seawater. Seawater intrudes in this area all the time over kilometers and is bringing heat that can interact with the ice and melt the ice. The ice is almost at 0 degrees there, and the melting point of that mixture is -2 degrees, so there's plenty of heat available to melt the ice. In the case of thwaites, we looked at the melting in this area using elevation data. We also look at radar thickness change. Radar thickness is more reliable because you see the bottom of the ice. Altimetry, you assume it's floating. And as I told you early on in this discussion, the ice is not always in hydrostatic equilibrium, especially downstream of the grounding line. And when the grounding line retreats, that deviation from flotation can also change. But in this particular sector here at the center of Twigs Glacier with fast retreat, we recorded melting rates of 200 meters per year, which are probably at the upper hand of what any ice sheet modeler has been using or daring to use to model the retreat of Twigs Glacier. And in other areas like Point B, melting is only 12 meters per year. And along the eastern ice shelf, it's 40 to 50 meters per year in the grounding zone. Now, we don't have enough details in the time series to tell you exactly how fast the ice was melting in the grounding zone. This is sort of a cumulative melt of the ice over some time period. And we cannot say that this melting occurred in the grounding zone. It occurred just in the wake of the retreat. We can't quite separate these two. Now we get a little bit more answers when we look at glaciers without an ice shelf. It solves the problem of scuba diving beneath the ice shelf. We can use acoustic devices, multi-beam, echo sounding to image the seafloor. And in the case here of this glacier, which is Store Glacier in Greenland, image the submerged ice face of the glacier and look at its shape. And I have a different color rendition here. This is an old movie. First showed that in 2015. Guys, I recycle my slides all the time. This is a little animation of looking at the ice face below the water line. This is the seafloor in front of Store Glacier. And this is represented as a point cloud instead of a surface. It makes it a little bit difficult to look at it like this. So when you rotate the picture, you can see a little bit more the geometry at hand here and particular shape of the front of the glacier. And you can probably notice the undercutting in a lot of parts of the glacier, but the undercutting becomes a little bit more dramatic if you look at this view from above. So in white here is pretty much the position of the ice front at mean sea level. And you see that the multi-beam system is able to map the seafloor inland of that, right? So all these pieces here of seafloor that are mapped below the vertical extension of the ice front correspond to areas where the glacier is being undercut. And the undercutting in this area is 100 meters, over 83% of the ice front, and in some place 350 meters. So it's prevalent almost across the entire glacier. We see it more, the maximum at 350 meters is an area where there's subglacial water coming out, and we know that the melting is more intense because the thermal airline circulation is more intense in this area, but it's also pervasive across the whole glacier. We've imaged a lot of glaciers like that and always found evidence for undercutting. Now this was, of course, confirmed by a model, and this is modeling study by my PhD student Xu Yun, which was done about 8 years ago. This is a modeling using the MIT GCM ocean model. So this is not a plume model with simplified equation. This is a full resolution ocean model with a 150 meter wide ice face, run at 1 meter resolution so you can reproduce the turbulence of the plume as you see here in the animation, non-hydrostatic conditions, and 3D. And we run a bunch of simulation where the subglacial water that you see here being discharged in red is not dispersed in one cavity, but in the distribution of cavity, different shapes, different spacing. it does not actually change the result of the melt rate so much. It introduces about 15% uncertainty. So we run that for different glacier depth, different thermal forcing, and different influx of subglacial water. The subglacial water is provided from surface melt upstream and basal friction and collects all at the grounding line of these glaciers. And we're able to find a parametric form of this, which is hard to read here, but the melt rate depends on water depth, the subglacial flux, and thermal forcing, which is the difference between the temperature of the water and the freezing point of seawater. It's a less than linear relationship versus subglacial. So subglacial is not the main driver, and it's above linear for thermal forcing, slightly above 1. What is represented here is an equation describing the peak melt rate, because what we found from this model is that the melt rate is not uniform. It's actually at its maximum close to the bottom, not quite at the bottom, but it undercuts the glacier. The highest melt rates are there. And if you look at the impact of this melting on the force balance, the average melt rate over the ice face doesn't matter. The total meltwater production from the glacier does not matter at all. What matters here is how much the glacier is undercut. So what you have to look at in that case is the maximum speed of melt at depth from the ocean and how it affects the glacier. And there's a factor 2 to 3 difference between the average melt and what I call the rate of undercutting of the glacier. So it's important to represent this process correctly by using the peak melt rate. Otherwise, you will decrease the influence of the ocean by a factor 2 to 3. So now we apply this to, we're going to look at this in the Northeast Greenland to Zachary Strom 79 North system. They both draining in this ice in the same climatic regions. They are reaching the same Arctic Ocean, same sort of ocean temperature. Zachary Strom lost his ice shelf. Nilgatsfjords Fjord did not. Part of the reason why is because it's the ice shelf in front of Nilgatsfjords Fjord is tied down by a set of islands, not like Zachary. But there's some other potential reasons why they changed so dramatically. Zachary lowered by 50 meters in 40 years. Only a fraction of that is due to surface melt. It's sped up by 80%, and it has been undergoing a 13-kilometer retreat over that time period, 40 years. 79 North, only 12 meters lowering, most of it from surface melt and not much speed up. And you see that Zachary Strom, which is shown here, lost his ice shelf. A cavity formed during the loss of the ice shelf that continued to grow with time until there was no ice shelf left. And even with near vertical ice face left in front of Zachary, we see some sort of undercutting here in the radar echoes in front of Zachary Strom. If we look at the detail into a radio echogram that I made in this region, it's really difficult to image properly the grounding zone. And if this undercutting, actually, you could not see it with radar echoes because they won't go through the water. But in all the radar echogram that we look at, we always find a rather sharp transition boundary in thickness. Well, here this is a vertical face, but we always note a sharp transition boundary right near the grounding line once we know the bed, which is reminiscent not of a vertical wall, but certainly not of a horizontal interface. So we did a lot of work in this region. There was a lot of work also done in front of 79 North by Janine Schaffer and others over many years to map the front with multi-beam. Here we did not collect multi-beam, but we collected airborne gravity to reveal a trough that makes a natural passage for the subsurface warm water to reach Zachary Strom. 79 North has a little bit more structure here that blocks the inflow of ocean heat. There's only a narrow passage in the middle that lets the ocean heat come in. This is a profile of temperature along the blue line for 79 North and for Zachary. There are some sills that block the warmest, deeper water. For Zachary, they are located over here. For 79 North, the most important limitation is just in front of the glacier. We look at all the existing CTD data in this sector. In this area, Wilson and Stranio showed that the circulation of the water is clockwise. You have Atlantic water coming from Northwest Trough that reaches 79 North, and Zachary Strom is not coming from the north. That water is currently above 1 degree, so it's very warm. It's several degrees above the freezing point of seawater. And using this CTD data and averaging the data over about 40% of the water column, the lower 40% of the water column, because this is what the model suggests is affecting the glacier, we get a warming of 1.3 degrees over these 40 years. This is the documentation of the grounding line retreat for 79 North and Zachary Strom. To go back to the 70s, we used DEM, and we validated our method when we have both DEM and interferometry. And we have a 13-kilometer retreat for Zachary and only 4 kilometers for 79 North. So on the left, you see a reconstruction of thermal forcing in green from 1.5 to 3 degrees. You see a reconstruction of the thinning from time series of DEM in meters per year, reconstruction of runoff from the Rignot model to model subglacial discharge. And then we calculated how the undercutting evolved for Zachary Strom and how the impact of thinning forced the grounding line on Zachary Strom. So the impact of thinning is shown in red here. The impact of undercutting is shown in blue. And the total grounding line retreat is the curve behind, which is color-coded gray. So if everything works, blue plus green plus red should match the gray, and that's the case for Zachary. And you see that the largest component is from thinning of the glacier versus undercutting. Undercutting increased from 100 to 180 meters per year, and the speed of retreat from thinning increased from 100 to 200. That's conducive to 13 kilometers retreat, and we sort of agree within 14%. For Zachary, for 79 North, QM is lower because less water is able to intrude, warm water is able to intrude in the cavity. The thinning is lower also because the glacier is not thinning as much, and it's retreating along prograde slope instead of retrograde slope as it is on the case of Zachary Strom. So you could call this a coincidence that the two processes together match the observed grounding line retreat. Fair comment, because we apply an undercutting model that was derived for vertical ice face, and we use it for 79 North, which has an ice shelf, and Zachary, which transitioned from the ice shelf system to the vertical face. You see that both processes contribute about 50-50. Taking the other way around, you could argue if we only use hydrostatic equilibrium, if we only use the thinning rate of the ice, we cannot explain the retreat of this glacier. We're off by almost 50%. And the difference is well above the errors we have in measuring bed slopes, surface slopes, and thinning. So something else is driving the system to a grounding line retreat of this magnitude, and it's not the thinning. The thinning, by the way, includes the surface melt. It includes the dynamic changes because the glacier is speeding up. It includes the effect of the ice shelf removal because that's conducive to speed up. It includes all of that. So this agreement between these estimates is sort of encouraging, in my opinion, that there is something going on at the grounding line, direct removal of ice by the ocean that is necessary to explain the observed transition. Now I'm going to move on to Humboldt Glacier, which I don't know if you can see the title, The Forgotten Giant. When I started my career in glaciology, I stumbled on two pictures, which were actually Landsat images for one and a radar image for the other, of glaciers. The first glacier I saw in Greenland from remote sensing data was Humboldt. It's a very impressive glacier. It's 100 kilometers wide. It's the largest glacier in Greenland. It's comparable in size to the largest glacier in the Antarctic. But it's also pretty sluggish. It moves at a few hundred meters per year. Most of the southern part of Humboldt Glacier actually hardly moves at all, less than 100 meters per year. It's mostly the northern part of Humboldt that moves fast and is dynamic and sends tabular icebergs into Kane Basin. And I never paid too much attention to this apparently sluggish glacier during most of my career. It was a forgotten picture. The other picture I saw was a Landsat image of Pine Island, and that one was more fascinating. Pine Island Glacier, the first Landsat image from the 70s produced from Pine Island Glacier was mesmerizing. A beautiful piece of art by nature with all the features that we could see on this glacier. But Humboldt was a famous geographer, as a basin that has a 20 centimeter sea level rise equivalent. It's not all marine, but it has a channel that connects to the deep interior that's marine. So it is part of the big submarine system in Greenland. It experienced a 4 to 5 kilometer retreat. That's the average retreat, but on this northern frontier, we're talking more about 12 kilometers since the 1960s. So a considerable retreat. It used to have a floating ice shelf. I saw that in the 1990s. I promise you that I saw that, and it's gone now. Unfortunately, I lost this damn data from my computer in a disk crash, so I have to regenerate all these interferograms. Of all the glaciers, if we look at the 40 years, this is the assessment from Mugino et al. It came at number 4 or 5 in terms of the largest loss in Greenland. Just because it's been losing mass all the time, these all 40 years, it comes to 160. You have to go to Jakobshavn and Kangerlussuaq, and I forget the name of these glaciers in central west Greenland that contributed the most. And Humboldt is right there. Big contributor, but we haven't talked too much about Humboldt, have we? We went there in 2019 with a boat and a multi-beam and imaged the whole front of the glacier. And the data actually shown here, it's a bit deceiving because on a 100 kilometer wide glacier, our little swath of the 2 kilometers seems minuscule and meaningless. But we were able to do the whole ice front, perfect navigation condition, in fact, in Kane Basin. I was very surprised by that. And realized that bed machine, the bed topography of Mathieu Molligam and others was 200 meters off in this sector. The bed was 200 meters deeper than what was reconstructed from bed machine. It was a big surprise. So rerunning the bed machine was not sufficient, would not be able to force bed machine to agree with this new boundary. But the model was revised using a new map of changing ice thickness with time over Humboldt, because this glacier has been thinning a lot for a long time, and using ISAT2 and GIMP to produce larger rates of thinning than what Mathieu had used originally. He was able to match the multi-beam data. And this is the new reconstructed bathymetry, which shows a trough that's 300 to 400 meters deep and extends quite inland. We don't have the full connection here, but there's an extension of that trough that goes all the way to Smith Sound at the edge of Baffin Bay. There's warm water coming in contact with the glacier here. How warm is this water? Well, this is not as warm as Zachary. It's certainly not as warm as what's happening in West Antarctica. It's about 0 degrees, but 0 degrees is 2 degrees above the freezing point of seawater. There's lots of CTD that have been collected in Nares Strait. We focus mostly on the CTD data collected in the channel conducive to Humboldt and on the eastern side of Smith Sound, because Andreas Mencho showed with ocean data that there's an influx of Atlantic water along that boundary here, presumably moving towards Humboldt. He knows there's flux here. Most of the flux in Nares Strait is from the north, Arctic cold water coming along the western boundary, which is Canada here, and flowing down into Baffin Bay. So for Humboldt, Atlantic intermediate water at 0 degrees, we have a warming of about 1 degree in 40 years from the CTD. The undercutting increased from 87 to 153 in the north. We separated the north from the south, and then look at the whole glacier to see if it was making a difference. You see that the increase in undercutting is almost the same in the north and south, even though the south is sort of bathing in shallower, colder water. Undercutting in total forced the grounding line retreat of 2.3 kilometers. And the thinning forced it by 0.4 kilometer in the south, 1.6 kilometer in the north, and about 1 kilometer total. And the total retreat is 2 kilometers in the south, 4.6 in the north, and 3.4 on average. Now, 3.4 is average over 100 kilometers. And as I showed you before, the retreat was not uniform. It's much more pronounced in the north. And there again, this is the forced retreat from thinning. And this is the observed grounding line retreat. The grounding line is the same as the ice front for Humboldt because there's no floating extension anymore. And we know that for sure. And you see there's a big gap in between. And that gap is filled if we use this undercutting model. This is for the northern ice front here. And this is for the entire ice front here at the bottom. So there again, it could be a coincidence, but it's also, as a matter of fact, that thinning of the ice is not able to explain what's happening to the grounding line. In ice sheet models currently, that QM process of undercutting is not there. We actually run it for modeling of a Twigs Glacier. That was the paper by Hongyu. It did not have as much impact on the retreat rate as is expected. That's for thwaites. But in general, in ice sheet models, melting at the grounding line is not allowed. And clearly, if that process is not included in the ice sheet models, you may argue that it's not real, it should not be there. It needs to be more validation. That's a fair comment. But if it's not in there, you're not going to be able to reproduce the rate of retreats that you observe. You're going to be off by a factor 2. Well, that's a big difference. And in fact, the thinning itself is not completely strange to what's happening in terms of undercutting. It's a result of the acceleration. So if you don't get the undercutting, you're not going to get the acceleration. The thinning will also be underestimated. So this is sort of my last slide. Going back to the origin of this talk to figure out what's happening at the grounding line and reflecting upon all the work we've been doing in the past decades looking at these glaciers and getting more and more screaming clues, in my opinion, that critical processes are taking place right at the grounding line. I would even argue, I don't care what's happening later on the floating part of the ice shelf. It's not even relevant. What's happening right there in this transition zone where these people are having a good time, they even serve alcohol, I see, is what matters. And it's the most challenging for us to study. This little cartoon here, this little video is our departure from Peterman Camp. And the person you see twisting his head to let the airplane fly off is Connie Steffen. Now, if I may, I'm going to terminate this talk in style, try, by singing. I want to be a rock star, so I put my rock star glasses. Keep on walking at the grounding line. 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 That's probably more than your ears can bear. So my talk is finished. Thank you very much for your attention.
Wow, thank you very much, Eric. So, lots of clapping and comments on the chat there. Are there any questions for Eric other than to sign him as a rock artist for the post-lockdown party?
Thank you for the cheers, people.
Maybe I'll start with a science question. I was wondering what you, whether you have any feeling what the melange in front of the big glaciers like Helheim and Kangerlussuaq does to the processes at the front, at the ice front. Most of the ones we have managed to get to in Greenland as a community are the ones without the ice melange there.
Oh, Helheim, you talking about Helheim?
Yeah, Helheim, Kangerlussuaq, the big southeast Greenland ones with kilometers of rubble in front of them.
That's a good question. These fjords are so hard to survey, as you know. We've not been able. These are the last resisting foes in Greenland, Helheim and Kangerlussuaq. The fjord is not been mapped very well. Helheim has this calving mechanism of rotating ice blocks, very impressive, which is also very intimidating. I don't think I want to do any work close to these glacier fronts. I think the Kangerlussuaq and Helheim, it's also valid for Jakobshavn. An aspect that I've not talked about too much is the speed of undercutting. And the speed of undercutting is pretty much limited by the thermal forcing. And it's typically difficult to envision a rate of undercutting at the current ocean temperature that exceeds 2 meters per day, 3 meters per day. And some of these glaciers, the fast-moving glaciers, have advection rates that are much larger than that. So you can consider that in order to dislodge these glaciers from their stable points, you really need an enormous amount of increase in undercutting because the advection is so large. In the case of Store Glacier, where the advection rate is also very large, I think it's probably 10, 12 meters per day compared to 2 meters, 3 meters per day of undercutting. An additional complication is that the glacier is calving on a ridge. And so in effect that undercutting, if it affects parts of the glacier that are already starting to flow, that are extending from the ridge, the glacier won't feel it. So there may be situations like this on Helheim or Kanger, we don't know, where the glacier is actually grounded slightly on the ridge. And the ice extending from that ridge, even though it may be in contact with ocean waters and melting rapidly, even very close to the ridge, may not make a difference. The glacier will still be driven by calving mechanism and will require a lot warmer ocean temperature before it can be dislodged from that ridge. So there again, I think the details of that bed topography is absolutely crucial. We went around Greenland. This is the work of Michael Wood, who's probably online, looking at all these glaciers. And we found that a lot of them that are flowing very fast or are calving on ridges basically don't care much about the ocean warming so far.
Thank you. Celia Martin, do you want to go next?
Yeah, Eric, I wanted your comment
on.
Hi, Eric. Nice to see you.
Nice to see you.
How close are we for thwaites to being on a runaway reverse slope?
Sea ice? I didn't catch everything, Celia. I'm sorry.
How close is Thwaites Glacier to being on a runaway reverse slope?
Oh, that's the trillion-dollar question everybody is trying to answer on the Twigs Glacier project. You know, Celia, there's only another sort of significant ridge upstream of Thwaites that could slow it down. And depending on the ice sheet models that you see, it could get stuck there for a little while or for several decades. It's not clear. It's a very sensitive area. Once the ice retreats past that ridge, which is, I think, if I'm correct, about 30 kilometers inland, I have not seen a model that predicts the stable state for twigs. After that, it's going to disappear like slippery soap. Personally, I don't think that ridge will stop the retreat at all. It might slow it down for a little while, but we've seen similar instances in the past where the glacier slows down a little bit its retreat, and once it passes the ridge, it keeps going. There's no change in the thermal forcing. If anything, the thermal forcing will keep going up as the winds keep pushing more ocean water on twigs. So as far as I'm concerned, I've seen enough for the past 10 years to say that we're on a trajectory to lose twigs in Pine Island. If we just sit there and do nothing to our climate system, we will lose it. And I think it's going to happen in less than 100 years that we're going to go past that ridge.
Thank you.
Sasha Leidman, do you want to unmute yourself? And
yeah, hi Eric.
Hi.
Great presentation. I was wondering if the effects of calving and the turbulence that it causes has any effect of bringing in warmer water to the ice front and causing melting, and therefore if faster glaciers might have more of an effect of bringing in that warm water.
That's a very good question, a very good point. We stumbled a little bit on that with Michael Shotlock doing some modeling of ice melt by the ocean in front of Twigs Glacier. Because if you remember, the Twigs Glacier used to have an extension called the Thwaites ice tongue, which had a few places where it was touching the ground, so very shallow water column. And Michael was saying that that piece of berg in front of the glacier has a huge effect on the advection of warm water on the glacier. I hear something, maybe from Francisco. So the presence of icebergs in front of the glacier surely disrupt the ocean circulation. It surely has an impact. I would tend to think from the modeling study of Shotlock that it tends to actually protect the glacier from the intrusion of warm water because it blocks the access to the grounding line. Now the steering of the water column from the calving events might do something different to the ocean circulation. I have not thought about that too much, but that's a very good point. Most of this modeling conceptualization here is assuming a clear fjord with no iceberg. And as you know, some of these fjords, they have almost always icebergs in them and in front of the glacier.
are there any further questions for Eric? I'll just check Facebook.
Less than 100 years per year. It's mostly the northern part of
Facebook.
I didn't hear.
Sorry, now I've cross-contamination of the two.
Go, Tim. I hear you.
So I think they're in. Oh, Tim, go ahead, Tim. I'm going to try and stop the cross-contamination of the two. Tim, go.
Tim, I hear you.
Okay, I'm hearing some feedback, but Eric, thanks for that talk. I was wondering if, as you think about this broad continuum of marine terminating glaciers from the kind of thin, narrow glaciers in Alaska terminating in 100 meters of water to Antarctica, where you've got these 100-kilometer wide, very deep termini, do you think that there's also a continuum of the importance of submarine melt? For which glaciers do you think submarine melt is really critically dynamically important? And do you think that there are potentially settings where submarine melt might be much less important?
You know, that's a very good question, Tim. Actually, I never thought about that, but in Alaska, where the water temperatures are so much higher, I think we're talking about water temperatures up to 7 degrees in some of these Alaskan waters. But but there's also enormous impact of surface melt, and ice is more brittle, more susceptible to calving. I would have thought originally, oh wow, the ocean is an enormous impact on the glacier, and yet what seems to be emerging from these studies is that the fastest retreat rates of any glaciers on Earth are not happening in Alaska. They're not even happening in Greenland. They're happening in West Antarctica. They're happening in the coldest part of the planet. They're also happening on glaciers that still have an ice shelf. The ice shelf in front of Pine Island is not in good health, but it's still there. The ice shelves in front of in front of Smith and Kohler Glacier are still there, pretty much unchanged. And yet we see retreat rates in these glaciers above 1 kilometer per year. Smith is retreating at 2 kilometers per year. We have a paper in review where we have evidence for duration of retreat of these glaciers at 3 kilometers per year. In Greenland, the glaciers are retreating about 0.5 kilometer per year. And let me be a little bit casual about this and attribute everything to the ocean. And the retreat rates that you have on glaciers in more temperate regions are smaller than that. So the fastest rate of retreat on Earth are happening in Antarctica. They are happening in the coldest part of the planet. So presumably because when you just put a little bit more heat into that system, it's very sensitive to that, as opposed to a system which is already pretty warm and you just put a little bit more warmth to it. So it's going to increase by 1 degree, but it was already 7 degrees prior. Whereas for a system like Humboldt, if you go from 0 to 1 degree over 40 years, that's a huge bang in the nose. So we do see a continuum. I think the validity of looking at glaciers in Alaska is that it shows us everything on a fast pace, and we get big numbers. So in terms of instrumentation and measurements, it's very important to do that on the warm glaciers. In fact, all this work on undercutting and action of the ocean on the glaciers started in Alaska with the work of Roman Motika. I used to call this paper from 2003 the paper of the decade. Roman was sort of embarrassed by that, or I don't know if he was taking me seriously, but even today I'll say that was the paper of the decade to me. And it started in Alaska. There's been a lot of great work also recently by David Sutherland in Alaska. But eventually, that knowledge is most useful for us to understand what's happening in the coldest part of the planet, and that's North Greenland, that's West Antarctica. So the lesson learned carry along the way. And to answer your question, I do think that these processes carry the most impact on the coldest part of the spectrum of the glaciers.
Great. Thanks, Eric.
Any last questions for Eric before? Pete Nino.
Yeah, hi Eric, thanks for your talk. In terms of sort of going forward and trying to model, say, the response of Greenland in the future, do you think that we are really in a position where we can really model the detailed calving processes, given how complex they are? Or do you think at the moment we need to try and do simpler parameterizations, which kind of blend the processes together, but that might get a better result? Or do we really need to take into account the real details of the mechanics?
That's a good question, Pete. Well, I think we made a big progress in Greenland in terms of mapping bathymetry in the fjords. It's kind of a giant step forward. We're sort of trying to finish the unresolved glaciers. So in terms of bathymetry for modelers and constraining ice thickness at the front, huge progress. I think the data sets that modelers have now in their hands, and I mean now, it's like a year old, are really good. The challenge is to apply the proper ocean thermal forcing on these glaciers. We don't have ocean models that run at high enough resolution right now. The global ocean models are very coarse. They cannot model what's happening on the continental shelf and they cannot even conceive doing anything in the fjords. You have to run at 1 kilometer or less resolution. So we're not quite there. But that doesn't mean that the ice sheet modelers cannot use some proxy from the outer ocean and use some connection between the outer ocean and the fjord, and use the proper barometry to make some giant progress. How to model what's happening at the grounding line? I think it's an open question. I threw my 2 cents today. A lot of other people are working on this. This undercutting model we have is one model. There's different ways it could be done. I don't know the ultimate way. But I'm pretty sure that if we don't represent that process at the grounding line of Greenland, it's going to be very hard to match the observations. And if we can't match the observations, if we always underestimate it, we should be cautious that this projection we have for the coming century are probably underestimates. And we should acknowledge that systematically, that we think it could be faster than that would be more appropriate than this is what it is, man. Antarctica is much more difficult, and I'm a little bit more concerned about the Antarctic. We have great data in the Amundsen Sea sector, thanks to all these international efforts. But in East Antarctica, especially the Wilkes-Land sector, there's some places where there's never been any map, no CTD, no bathymetry, and we see some changes from the satellite data. So there, I'm a little bit concerned that progress is going to be limited until we have some international efforts to go get those critical data.
Any last?
After that, it should be a lot of fun things for ice sheet modelers. I mean, your golden age is coming up, guys. You've been polishing your tools. There's some really nice tools out there, and golden age is right there.
Any last questions? Can I ask you to move to your last slide, the last slide?
Yes, absolutely. Let's see. Here we go.
So this is just to advertise next week's seminar, where we've got 3 early career scientists giving shorter talks. So basically, I should say thank you very much indeed to Eric, and if everyone would like to unmute and give him a round of applause, that'd be amazing. And hope to see you next week for the 3 talks you see advertised on your screen from North and South Southern hemispheres. So thanks very much, Eric.
Thank you, Tavi. Thank you, everyone, for coming.
No.
Thank you.
So thank you very much indeed, Eric. That was brilliant. And see everyone next week. You're getting lots of thank yous on the chat, so I'll leave those to pop up.
Oh, yeah.
Okay, so see you all next week for the next seminar.
Thank you.